first talk in the series of lectures on property T for automorphisms of T groups by Marek Kaluba from Karlsruhe Institute of Technology.
Thank you very much. Thank you very much for the invitation and for everybody who joined today. This is the first of the two lectures about property T for the automorphism group of the free group. But I will not be really focusing on the automorphism group. I will be focusing more on the general technique and leave the automorphism groups for Piotr for the second. All right, so this is a joint work with David Kielak, Piotr Nowak, and Naru Takaozawa. And we were going to start very simply by asking ourselves what positivity is. And then we are going to discuss some practical matters. Then I'm going to give you a definition of property T, which is tailored specifically for this lecture, so it's not going to be a general introduction to property T. And then will be some examples, and maybe, if time permits, we're going to see some later topics. All right, so positivity. So here's an introductory question. We start with a polynomial, very simple object, real polynomial, f in one of several variables, and we want to ask when f is a globally non-negative polynomial, right? And we can see very clearly that it's very easy to refute the claim of positivity. I mean, I find one point where the value of this polynomial is negative, and then we see, okay, this is not non-negative. But the question is, does there exist a witness that is also going to be so easy to verify that is going to prove to us that this polynomial is positive or non-negative? I'm going to use positivity and non-negativity as a synonym, but right? So we have these two. We can look at this from two different sides. One of them is analytic. We look at polynomial not as an element of the ring, but as a function, and then the values determine the positivity or not. Or we can look at polynomial as an algebraic thing, and then the question is there a structure of this polynomial that are going to tell us this polynomial is definitely non-negative, right? So as I told you, it's very simple. So we begin in the secondary school. We have this beautiful polynomial, ax squared plus bx plus c. And we clearly know that this guy is going to be greater or equal than 0 if these two algebraic invariants are satisfied. Very well. And we can also say that a polynomial f admits a sum of squares decomposition if f can be written as a sum of squares of some real polynomials. And of course, if I can find such a decomposition, then f must be non-negative. And of course, one is just the other thing, because if I have this polynomial, I can write it always like this. And this is going to be a sum of squares of two real polynomials, if and only if, and then I have to see, oh, a has to be bigger than 0, and this guy also has to be real. So it's the same thing, really, it's the same thing. Very well, and like this problem of asking if a polynomial is positive or not is not very new. Hilbert in 1888 asked the same question, and he also found the necessary and sufficient conditions, namely a non-negative polynomial is a sum of squares. So this is my notation, or the set of sum of squares. If and only if it's a univariate polynomial, or it's a bivariate, or it's a quadratic polynomial in arbitrary number of variables, or it's a bivariate quartic, so there are two variables and the degree is 4. Okay. So you might ask, so are there any examples of, let's say, 3 variables or 2 variables and degree 6? And here's an example. We take x to the fourth y squared, x squared y fourth, minus 3x squared y squared plus 1. And this guy is non-negative, which is also a high school exercise. But it's not a sum of squares, which is maybe a more advanced, but not really that hard, right? What I would like to point out here is the different dates, right? So this is 1967, this is 1888. Hilbert proved the existence of those polynomials, but he didn't find a single one, which is deceptively simple. And just to finish this part of the story is that the full theorem or the full solution to the Hilbert 17th problem was given by Artin, who said that an everywhere non-negative polynomial P is a sum of squares of rational functions, which might look strange. What does it mean? A polynomial is sum of squares of rational functions. But you should think of this that there is some kind of, if I multiply by all of the denominators in this sum of squares, then I'm multiplying by something that is already a square. So that means that if for every such a polynomial, there will exist another one, which if I multiply by the square of it, it will become sum of squares. And here is a simple example. If we take this Motzkin polynomial and I multiply it by x squared plus y squared plus 1, it becomes a sum of squares. Nice. Maybe even surprising. And for me, it's even still surprising. All right. So we have these two flavors of positivity. One is the analytic positivity. When we look at values, we are going to see what is going to happen to this one. The other one is algebraic positivity when we look at sum of squares structure. And there's a whole genre of theorems relating one positivity to the other. The first one was started by Hilbert, which is which we have seen. But they are in general called Positivstellensätze. They could happen in different rings or in different algebras. But they can also, we started with saying f is a globally non-negative. But what happens if I want to say this is a polynomial that is non-negative only on a fixed algebraic? So there is a whole theory behind it. And now this difference in dates that we have seen is the next thing that I want to address. Namely, in this talk, I'm really interested in practicality. So it's not only that I want to prove the existence, or I want to prove that some of them are. No, I have one particular, or will have one particular polynomial, and I really want to find one particular sum of squares decomposition for this guy. So the question is, how do we do it? And one of the ways is through linear algebra, right? So sometimes it is possible that if I have a polynomial, I can write it as a quadratic function of monomials. So what does it mean? That means that I have some bases consisting of monomials, and then I have some matrix inside here, and then I have the same basis transposed consisting of monomials. Now, this is here only a sub-basis. Most of the entries in this matrix will be 0, so I just pick the non-zero ones. And then I can write this polynomial as, well, quadratic form with this matrix associated to this basis. And we can see here that this matrix has 1 degree of freedom. I mean, I picked this polynomial so that it is constructed like this. And this matrix P is going to be called a Gram matrix for this polynomial with this basis. And the very simple lemma from linear algebra says that polynomial is a positive definite quadratic form or admits a sum of squares of decomposition if there exists a positive semi-definite Gram matrix for some basis for this polynomial. And here what happens is that I have this Gram matrix, and I specify, okay, let me pick lambda equal to 6. So this is this one. And now this one is positive semi-definite, so I know that there exists another matrix Q, so that QT, Q is equal to P. So this is my matrix Q. And out of this matrix Q, I can read off my sum of squares decomposition. Namely, I just look at the rows of this matrix, and I look at the bases, this one, and I evaluate those guys, and then I say, I see that this is 2xy plus y squared. So this is the first one, and the second row is the second. It's very simple, very straightforward. All right. And of course, Q is not unique, especially in the rank deficient case. Here we see that this is rank deficient. So maybe one more thing that I want to say is that the number of squares equals to the rank of Q. The whole story here is that I'm given something that looks like a polynomial, and then I treat it as a quadratic form, and then the whole thing is about searching for the right basis, in which the ground matrix, a ground matrix for this polynomial is positive semi-definite. All right, so how to do it in practical terms? Because this is a contrived example, namely I picked the polynomial, well, no. Truth to be told, I picked the sum of squares decomposition and I reverse engineered everything, right? But normally we start with a different thing, right? I'm given this polynomial and the question is, can I find it? So how do we do it? And of course, we are not going to look at polynomials that are 5 coefficients. We are going to be looking at polynomials which are huge. And one tool to do this is to do mathematical programming. So what is mathematical programming? It's a general term to describe some convex optimization routines. One of them, probably the best well-known, is linear programming, when we want to optimize a linear functional over a set constrained by hyperplanes. Okay, so this set is called polytope. And then there is a second iteration of this one, more related to metrical things, when we want to optimize, again, a linear functional on a polytope, so set constrained by hyperplanes, intersected with a cone of a PSD matrix. What does it mean? I just want to say, some of the unknowns are going to form a matrix which I want to be semi-positive definite. And this semi-definite programming is something that we'll use to find those sum of squares decomposition in large scale. So here's a text, because if you've never seen this, then it might look very abstract, but it's actually very simple or very concrete. So here is a textbook's definition. So what I want to do is I have this set of variables, P, which also can be also forms a matrix, and I want to maximize some linear functional. So this is a dot product. And then I want to say that this matrix is positive semi-definite. And then I want to say that, if I take those unknowns P, and I, again, dot product them with some other known vectors or matrices, then I get some known values. And again, here's the same thing. We have this polynomial. And then we say, is it always non-negative? And we relax this question to the question of, does there exist a sum of squares for this polynomial decomposition? And this one corresponds to the existence of a PSD matrix P, such that our polynomial can be written as a quadratic form. Okay? And here, what are these objects here? So for example, if I look at this xxt dot p, and I look at xxt, and this gives me all possible monomials, or products of two monomials. And then what I want to say is that, at x to the 4th, f is equal to 4. So this matrix is going to select this one entry from my P, which is 3 by 3. And I'm going to say the first entry of this matrix, it must be equal to 4. So that's precisely It's very concrete, very simple, very easy to ng. All right. Now, because we are dealing with property T, we have to leave the simple world of polynomials, where everything is commutative. And now we have to enter into the world of non-commutative things, right? Because we'll be dealing with groups, which, as we know, sometimes are non-commutative. So when we have a non-commutative algebra, not a polynomial algebra, but now non-commutative star algebra, what is the cone of sum of squares? The sum of squares, I can no longer write q squared or f squared because I have this involution, the star, in my algebra. So this is the proper generalization of this thing. And one should note that if I have an element here, then if I apply the star involution to it, it's going to stay here, right? Because the star is going to switch these two, and then star is going to cancel with itself. And if you see this definition for the first time, maybe you should think that if I have this positive semi-definite matrix P, it's not that P can be written as Q times Q. No, it's going to be written as Q star Q. So this is maybe some motivation why this is the proper definition. And now the question is, what is the proper notion of positivity when we look at non-commutative things? Right? And here we start with an example, and we say, you know, I have an element in this free polynomial algebra. So free polynomial algebra means there are no relations between variables, so they don't commute. And these are like standard finite sequences of coefficient times some monomial. And then I'm going to say that such an element A is positive. First of all, if it is self-adjoint. That's one thing. And the second thing is that if I take any star representation of this algebra, so that means that for every variable, I prescribe a matrix. Okay? And then I can evaluate this representation on this element, which means I take coefficients, which are complex numbers. I take those monomials, and I replace them with those matrices, or products of those matrices. And then I get an honest matrix at the very end. So then I can say this matrix is positive semi-definite. Okay? Is it clear? And here there is a small miracle, because this is really a miracle, that Hankel proved that A in this free polynomial algebra is positive if and only if it belongs to this sum of squares. And you may ask, wait, so we started with polynomial things, and in polynomial things, we know that there exists polynomials which are positive, but are not sum of squares. So why this seems to be, you know, stronger statement, right? Any idea why? Because in polynomial algebra, the only assignments to those variables of matrices that we should consider are the diagonal ones. There are very few representations of the polynomial algebra, right? All variables commute, so they are all direct sums of one-dimensional. But here, this positivity statement actually is much stronger. So of course, if we require something much stronger, then we get a much stronger result. All right, so this is what I said, that in polynomials, you know, we said that there is this evaluation of polynomials, and evaluation of polynomials corresponds precisely to those one-dimensional representation when I want to evaluate my polynomial at a given point. All right, so finally, this brings me to the topic of what is property. So the primary algebras that we will be dealing with are the group algebras for some finitely generated groups. And I'm going to assume that my generating set is symmetric. That means that it contains all the inverses. right? So what is this group algebra? You can think of them as finitely supported functions from the group to the real numbers that are written commonly as finite sums with the value at a given group element followed by the group element. The multiplication inside is convolution of two functions, which is a fancy way of saying I take such a sum, I take another sum, I multiply everything by everything and group together. And the involution on this group algebra is induced by taking G to its inverse and then extending it linearly while preserving the coefficient. So I have something like this. I invert identity, well, that's identity. I invert G, that's G inverse. I do nothing to coefficients, and so on. Right. And in such an algebra, there exists, for a finitely generated group, there definitely exists a Laplacian. And this Laplacian can be written very simply as an element of the group algebra. It's the size of the generating set times identity minus all of the generators. Or you can talk about normalized one or unnormalized one. This is unnormalized one because it's not a probability measure. So what I write here is not exactly correct, but up to constant factor it is. It corresponds to some lazy random walk on a group. So one thing that we should see immediately is that such a Laplacian is self-adjoint. Okay? I assumed that my generating set is symmetric. So whenever I apply star to any of this G, it becomes another element of the generating set. So this is fine. The second thing that might be not so easy to see is that this guy is already a sum of squares. Okay? And this this follows from a very simple, maybe this is overly complicated, but basically if I see something like this, G minus G inverse, this I can write as 1 minus G star 1 minus G. Okay? Because 1 here is actually this element of degree 2, whatever degree means in the group algebra, right? So it looks like it's linear function, like a polynomial that would be a linear polynomial, but in group algebra, it's actually no. Right? And then this is maybe a stupid remark, namely if I take this expression, delta minus lambda identity, so that's like an eigenvalue problem, and then I project it onto delta again. This guy is going to be non-negative, well, definitely for lambda equal to 0, right? Because for lambda equal to 0, this guy is going to be delta square, which is the same as delta star delta. Okay? So this is maybe a stupid remark, but I make it to say that this is 0, and this is non-interesting. But if there exists a lambda that is positive, that is going to be very interesting. Okay? Because such a lambda will be, I'm calling such a lambda the universal spectral gap of delta. Why? Because if I take this delta and I represent it through any representation of my group, then this lambda is going to be the lower bound for the spectral gap in this representation. And finally, we have the definition of property T that is for this lecture. I mean, it is a definition, but this one is tailored for this lecture. So we say that G has property T if and only if there exists a finite symmetric generating set. That's what we have. And the lambda, which is strictly positive, such that this element is non-negative as an element in the maximal C-star group algebra. So for those of you who know what C-star group algebra is, that's fine. For those of you who don't, it's a completion of the group ring. It's a completion with respect to some norm that comes out of those representations. Okay? it's not really that interesting, or not, it is very interesting, but not very important for this lecture to understand really this, this completion. But you have to understand that this positivity comes from evaluating those representations. And then there is a theorem that is essentially started all of this research that I'm describing today. Is a theorem of Narutaka Ozawa in 2014, where he said that delta square minus lambda delta is non-negative in C-star group algebra, if and only if the same element is non-negative as a group ring, considered as a group ring element. And then what he actually proved, what was the most important thing, was that delta square minus lambda delta can be written as a sum of squares as well, up to some small perturbation. Okay? And all of those three conditions are equivalent to themselves. Okay? So what is this small perturbation? You have to think of this small perturbation as follows. So the whole thing is my vector space, Rg. And inside it, there is a cone of sum of squares. Okay. And now I take, there is some topology here, called algebraic topology, corresponding well to the vector space we are in. And now I take a order unit, which is an interior point of this cone in this topology. And the problems here are that positivity can be also experienced at the border of the cone. Okay? And then what happens is that if I take this order unit, an internal point of this cone, and I perturb this element just a little bit in the direction. This is u, and then this is some psi, and this is psi plus epsilon u. Then it becomes an honest sum of squares. Yes. Yes. Yeah, it's a fair question. So for this, it's enough to look at not at unitary representations, but at orthogonal representations, and you can build. Yeah, and I think that here the non-negativity with respect to unitary is the same as on the level of the group ring. It's the same as with unitary and orthogonal are, positivity is the same. But I'm actually not sure. No, order unit, okay, so order unit is a name. Order unit. Okay, so it's not unit in the algebra. Order unit is just a name for saying it's an internal point of the cone. So the cone gives you some order. You can say that two elements, one is greater than the other if the difference is positive. So that means it's in the cone. So that is why it's called order. And unit, I'm actually not sure. So order unit is a different name for the internal point. So you can see here it's the same, well, it's not the same, but it's a similar story. There is some notion of positivity, and then we change it into some notion of analytic positivity, and then we change it into some notion of algebraic structure. Okay, maybe that's the maybe that's the. So here, yes, there is some any. That means that whatever order unit I find, it should be equally good. But yeah, with this, maybe we should. Maybe there is an assumption that there is some norm. Yes, a Dirac identity will be good. Yes. So. And maybe there is a slide that is going to say why this one is not the good one. But in particular, we see that this is property T, and then we see that this guy is going to be sum of squares. Okay? So this is the sum of squares we'll be looking for with some appropriate U. Right? Maybe there is not a slide with what I want to say, but maybe I actually don't know how much time I have. Not so much. All right. So property T, more examples. So we know that SLN Z has property T. That's a standard example. And then there was a question of a special automorphisms group or automorphisms group of the free group, which is a non-commutative analog for SLN. And it was proven relatively quickly that S out F3, S out F2 is essentially F2, so it does not have property T. But S out F3 was proven to have infinite quotient of S out F3 has an infinite abelianization. So it was proven by Matt Cole. And then there was this question if the S out Fn has property T. That was repeated over and over again over the years. And in 2017, with Piotr Nowak and Narutaka Ozawa, we found a constructive and computer-assisted proof, according to the lines I gave you, that S out F5 has property T. And then in 2018, with Piotr Nowak and David Kielak, we proved we lifted this fact to higher ends. This is something that Piotr will be talking about. But there is some very interesting recent development in 2020 and 2023. Martin Nietzsche, a colleague of mine from KIT, he actually right now has a very recent proof that S out Fn has T for almost all n without using computer. And here you have the reference to this paper. All right. So why do we even bother about property T for this particular group? Well, first of all, why do we bother about property T? There is a connection between the expanding family of subgraphs and residually finite groups with property T. Namely, we can construct one from the others. The unbounded size comes from the intersections of the groups going to identity. Bounded degree comes from the fact that we have fixed sets of generators, and the spectral graph of the Laplacian is bounded away from 0 uniformly because this lambda is going to be this bound. Okay. But also there is a different motivation that is particular to property T and automorphisms group of the free group. Namely, if we are after random group elements in finite groups, there exists an algorithm called product replacement algorithm, which is some form of a random walk. And we can prove that this random walk, the mixing time of this random walk can be estimated using this lambda for this special automorphism group. Okay? And you should maybe ponder this statement a little bit, because there is this one group with one lambda that tells you how quickly all the random walks are going to converge to the uniform one for all finite groups generated by n elements. Okay? So this is a very strong, very peculiar statement. Right? And it was observed for a long time that this product replacement algorithm has fast mixing time. All right. So this is the overview of the algorithm. We start with our finitely generated group with G and S. Then we pick some monomial bases. So this is a set of group elements. For example, we can pick a ball of radius D. And then we form this, positive semi-definite problem when we want to maximize our lambda with lambda greater than 0 and P to be positive semi-definite such that this guy, delta square minus lambda delta, is equal to this vector matrix vector product. So we write this one as a quadratic form. And this looks exactly the same as in polynomial case. The only thing that is different is that the linear constraints are somehow different because now they are no longer commutable. But that's a technical part. And after we've done this, we look at the square root of this P that we found, and we look at the columns and or rows, depending on whether we transpose or not. And as previously we have seen, those guys gives us vectors, which are coefficients in the bases, so we can reconstruct the sum of squares decomposition. Okay? And these were so simple, but reality is not so simple. So when we solve this problem numerically, this is never equality. So this is only up to some small discrepancy, and now we have to deal with this. All right. So how do we certify that these numerical solutions give us the actual result? Okay. So this is based on a lemma that was made explicit or quantitative by Netzer and Tom. Namely, if we have this cone and we have an element R here, which is very close in the one norm neighborhood of our cone, then we know how much we need to push it in the direction of lambda so that it ends up inside the cone. So that means it is a sum of squares. Okay? So it's a statement about dominating a small element in norm L1 norm by the delta. Okay? And if you look at this picture and you think, oh, this is obvious, well, then maybe you want to look at this cone. And then maybe this is what L1 neighborhood. And if you have R here and delta here, maybe this vector will be of infinite. Right? But here, this is kind of uniform. It's not called uniform convexity, but it has this flavor inside. Okay? So therefore, if we have a small r, so small discrepancy in L1 norm, then we can modify the sum of, well, modify the objective, and then dominate this discrepancy by subtracting some delta. Okay, so then we know that delta has not spectral gap of lambda, but actually lambda minus this constant times the norm of the discrepancy. Right, so then we have to modify our algorithms, because now you reconstruct the sum of squares up to some small discrepancy, and then we have to modify what we claim, right? So now we say that we no longer claim that lambda is the spectral gap, but we have to say there is some lambda that is greater than this. Okay? This is still not correct, but maybe I'm going to skip this one because I'm running out of time. Okay, so here's a baby example. If we start with the group of SO3Z, and we look at the ball of radius 2, the generating set are the elementary matrices, then I look at this matrix with some ordering of rows and columns, which corresponds to some group elements. And this matrix is a proof that SL3Z has property T with lambda equal to 0.28. Right, so there are a few numbers. Namely, we can prove SL3, 4, and 5 rather easily with pretty high lambda compared to what was known. So what was known before for SL5Z was something like this was a result by Martin Kasabov. So this is a substantial gain. But when we tried the same philosophy for S out of 4, we got 0, which might mean anything. Well, maybe the basis that we have chosen was wrong, or the subspace where we are looking for this basis. But when we tried S out of 5, actually it turned out that we couldn't actually solve this because it was too large, right? So then we thought there must be a better way. And of course there is one, because when we have this group, this generated by the set of all transvections or elementary matrices, if you want, then the original problem is to realize this one as sum of squares semi-definite optimization problem, which gives us this one huge positive semi-definite constraint and 11 millions of equality constraints. But then you realize that there is a finite group, namely this one, the Weil group, acting on this vector space. And you could decompose this space into the irreducible summands. And this PSD constraint, which is a matrix, right? It's an equivariant operator that fixes this space. So you can use Wedderburn decomposition to simplify this one huge PSD constraint. And then it turns out that there are 29 blocks of where the largest is 58 by 58. Right? And if you think about complexity, what we are doing when we are solving the PSD problems, we are doing eigenvalue decomposition. Eigenvalue decomposition, the algorithms are O of n to the cubed. So when we make 4,000s to 58, it's 1 billion times faster from the complexity. Okay, and now it turns out that you can solve this problem in 5 minutes with high precision. And this is the proof with Piotr Nowak and Narutaka Ozawa that out of 5 has property, right? So just to give you a sense of scale, so this was the final optimization problem. We are only looking at those values along the diagonal. This is the 58 by 58 block. And the original one was of this size, right? We are looking only at this small part on the left. And maybe I can just show you one last slide. Namely, the problems with this approach are the following. It's a black box solution. So we put it into the solver. Solver gives us a huge matrix. And then we analyze this matrix to make sure that this gives us an honest solution, but we do not understand this solution. We know it's there. So it's kind of existence statement. We actually, well, try to learn something about the solution. We know much more than we used to in 2018. But maybe more important is that it seems to be like once per group solution, right? So you give me a group, I can compute this, it's successful, and therefore we have property T, but you give me another group, I have to compute again, right? And this one will be addressed by Piotr in his talk, because the proof that out of n has property T is based on some kind of induction where we can actually localize what needs to be proved to out of 5 or SL3Z, and out of this one computation, we can derive the proof for all out of n's or for all SLN's. Right? Thank you very much for your attention.
Questions from the audience?
Yeah, so here it seems that I start with the group SL3Z. I look at its Laplacian, or Laplacian this one. I prove this happens, so that means that I've written sum of squares decomposition. Okay. But now what happens if I move to SL4Z? Like, can I use the old one to derive the new one, right? And a priori, on face value, there is no reason why the same thing or delta 4 why should this be related to this one, right? So every time you start with a new group, I have to do a new computation because those psi i's might be completely different, maybe unrelated to this. But what we proved in this article, which Piotr will be discussing, is that there is actually a way to relate one to another. And what is even more interesting, there is one computation that you can do in SL3Z, which is not exactly this one, but a different one. But you can still, out of positivity of certain element here, you can derive property T for SLNZ for every other n. And the same thing goes for out of n, and that's why this article is in existence.
Yeah, go ahead. Yeah.
It's preserved. So yeah, so it's stated as well, special automorphism group, but it's the same. It leads to out of n, and also it leads to any finite extension. Maybe what was not here clearly visible is that it leads to much more, in the sense, because I only look at a finite dimensional vector space of the group algebra. So if I can find a different group which has isomorphic those subspaces, and by isomorphic I mean not only as subspaces but also partially defined multiplication, so partially defined algebra structures, then you can lift one sum of squares decomposition into another. Therefore, this statement actually works not only for SLNZ, but also works for the Steinberg group, because we only use those few relations that are visible in small balls. It's not the standard way you lift property T, but here it is possible. Like taking, for example, Z of T. Is this the question? Oh, I don't know. I don't know. Yeah, but the question was, can we replace this R by something else, right? Yeah, this I don't know. This I don't know. I actually never thought about it.
Any further questions? If there are none, let's thank the speaker again.
Thank you. So we'll meet, we'll have coffee now, and we'll meet at 12 here.